Alright guys, so we're on Unit 9, Day 2, and this is where we're going to be talking about symmetry. And the first thing we're going to talk about here is line symmetry. A figure has line symmetry if it can be folded along a line so that the two halves match. Also, you kind of determine it can have multiple lines of line symmetry. So that's what we're going to talk about today, first and foremost, and then we're going to get into the other symmetries and talk about tessellations. So what's going to happen is for each of these, I'm going to do 1 through 3, and then you're going to finish 4 through 9. So the first thing we want to talk about is, does this shape have line symmetry? And so when I draw a line through this square here, is this side the same as this side? In other words, could I take this point and fold it over and get the same thing and like have it mirror on top of each other? And I totally could. But I can also do this and fold it on top of each other. I could also do this, and I can also do this. So if we were considering line symmetry to be question A for this, then our answer would be yes, and it has 4 lines of line symmetry. When we take a look at this triangle, it does have a line of line symmetry right there. Now, I know a lot of people have stopped before and said, okay, so it only has 1. The problem is with this triangle, when I turn it, I find another one. And then when I turn it again, I find one more. So in A for this one, it has 3 lines of line symmetry. Now, these were what we call regular polygons. Okay, a regular 4-sided figure and a regular 3-sided figure. It's when it's a non-regular figure that things change. So a rectangle is not a regular quad because it's not, the same no matter how I turn it. So the lines of symmetry is actually going to go down. Obviously, I can draw a line of symmetry here so that this half is the same as this half, and I can draw a line of symmetry here. Can I cut this rectangle any other way that would make this thing fold into halves? Well, if I try to go this way, when I pull this corner up, it's not going to touch this corner. And so when I do the rectangle, this one only has 2 lines of symmetry. So again, like I said, if it's a regular shape, usually the number of sides is the number of lines of symmetry you have. If it's an irregular shape, it's going to be less. Obviously, the most lines of symmetry that a shape could have would be equal to the number of sides it has. So go ahead and pause the video and do 4 through 9 and tell me how many lines of symmetry they have. Alright, so we've done the lines of symmetry for 4 through 9. As you can see here, this was a regular pentagon, so it had the full 5. Irregular quad, so it only had 2. Irregular triangle, so it had 0. There was no way to break this up so that both sides were equal. Number 7, again, an isosceles triangle, so you could get 1. And then irregular quad, so you could get 1. And then with the kite, you can get 1. So that covers line symmetry. The second thing that we want to talk about, does the shape have point symmetry? So this is going to be a quick yes or no idea. And essentially what point symmetry says is, if I have a shape, so in this case I have this square that looks like a diamond. If I turn my paper 180 degrees, do I still have that same diamond? Up, up, left, right. Up, up, left, right. So this shape does have point symmetry. Let's look at the triangle. The triangle is pointing up with the base angles at the bottom. When I turn this 180 degrees, is the triangle still pointing up? Well, no. And the base angles are now at the top. So this triangle does not have point symmetry. Let's look at the rectangle. When I turn it, it's still a rectangle, and it's still going horizontally. So the rectangle does have point symmetry. So what I want you to do again is look through 4 through 9, flip the shapes, and tell me if they have point symmetry. Hopefully you took a look at the shapes and determine if they have point symmetry. Point symmetry is pretty hard. I mean, they have to have a turn of 180 degrees in order to do that. The only one of 4 through 9 that did was this one. Okay, all the rest of them, when you turn them this way, you get a different shape. The only one that is the same shape when I turned it onto itself was right here. And so that goes into our third thing, a rotational symmetry. A shape has rotational symmetry when it still looks the same after a rotation of less than 1 full turn. Okay? And so how many degrees does this shape have to turn to the point where it looks the same? Well, if I turn it 180, we know it looks the same, but let's go ahead and turn this thing 90 degrees. It still looks the same. And so with the quadrilateral, it's 90 degrees to get this shape to look exactly the same. And the way that we did that, and we've talked about in the past, a circle is 360. So 360 divided by 4 is 90 degrees. Okay? How many times can we turn this shape and have it look the same? Well, 1, 2, and 3. So 360 divided by 3 is 120 degrees. With the rectangle, we get, again, 360 divided by 4, because, well, actually, wait a minute. If I do that, oh, it's not there. There it is. It's only 1 and 2, so it's 360 divided by 2. That's 180 degrees rotational symmetry. With the pentagon, well, 1, 2, 3, 4, 5. 5 turns to get back to the original shape. 360 divided by 5 is 72 degrees. Now, if you can't turn the shape and make it look the same, then it doesn't have rotational symmetry. Okay, so if you turn it one time around and that's when it finally looks the same, then it doesn't have rotational symmetry. So I'm just gonna walk you through. Obviously, number 5 still has rotational symmetry. Again, it's an irregular, so it's going to be at 180 degrees because it's going to take a half a turn to get it all the way around. Number 6 does not have rotational symmetry because you're never going to get this picture until you get it all the way back around to where it is. Number 7 also does not have rotational symmetry. You're not going to get this picture until you turn it all the way around. And as you can imagine, the same goes for 8 and 9. So this covers symmetry. Symmetry is a pretty easy idea. It's basically how does the shape look the same, whether I split it in half, whether I flip it 180 degrees, or how far do I have to turn it to get it to look the same, okay? And so those are the 3 different things. And really, like I said, it's quick, it's easy, it's something to be able to do, to basically say, how does the shape divide or map onto itself based on whether or not I divide it or turn it. The last thing I want to talk about is tessellations. You'll sometimes see the word tessellations when you come across symmetry and transformations. And tessellations is essentially a fancy word for tiling. And the idea is, what are the shapes that we can tile? Well, obviously, like if you guys have ever been to a house and you've looked at the floor or a tile on a wall, most tiles are a square. You can obviously tile a rectangle. You can tile a just pretty much a square and a rectangle. So The idea is that you can tile a quadrilateral. You can also tile a triangle, because if you notice, when you tile a triangle, you can flip it to end up with flat edges. And that's the key, is that you can flip it to end up with flat edges. Now, when I ask people, or I tell people there are 3 different shapes that can tile, they always try to say, oh, well, the next one's a pentagon, because they think of like a soccer ball. The problem with the pentagon is it doesn't create a flat edge when it's all said and done. And so a pentagon is actually not one. Think about a soccer ball is it's round, and so the pentagon can actually be made up to make a round shape. But when we're talking about a flat shape, we actually need to have a hexagon. And the reason being is because a hexagon can fall right into place and create, and I'm a really bad drawer, but you get the point. A hexagon can create, and you can keep building the hexagon. It's kind of like if you've ever noticed, like honeycombs from bees, they seem to be like of a hexagon shape. And so the 3 shapes that can tile or tessellate are a quad, a triangle, and a hexagon. And those are the ones that you're going to see the most often when we talk about angles and shapes in the next section. Alright, so that concludes the notes. What you're supposed to be working on for the rest of this section, again, because it was such an easy section and I wanted you to be able to move on quickly, is, and I'm going to go to the unit plan. So day 2, in the workbook, you're going to be working on page 235, 1 through 23, and then 237, 1 to 5. And then you're going to complete the day 2 review. So again, because this was so quick, I just wanted you to be able to get to it quickly, and hopefully do well with this material. So when we go to 235, again, on 1 through 8, you're going to say, does it have line symmetry? Does it have point symmetry? So you're going to do the same thing we did for 1 through, you're going to do line, point, and then does it have rotational symmetry? Okay. 9 through 12, it just says, how many lines of symmetry? They're all regular, so it's pretty easy, based on what we talked about before. 13 through 23, again, this is what we talked about in the notes, and so hopefully you guys understand this question pretty simply. 15 through 16, I just want to know, does it have rotational symmetry? And you should be able to answer that pretty quickly. And then again, 17 through 23, I want to know, does it have rotational symmetry? Don't worry about reflectional symmetry. That has to do with, can I divide it in half? And I don't want to spend a whole lot of time on that. Okay. Then you're going to go ahead and answer questions 1 through 5. And then when you're done with those, you check off with me. You are going to do the Unit 9 Day 2 review. Make sure you focus in on the reflections and translations, and you'll also get some extra practice on the symmetry stuff that we just did today. Any questions, see me, and good luck.